Hi everyone, and thanks a lot for coming here for this video abstract on our recent paper, Switchable spin-photon coupling with Hall spins in single quantum dots, that was recently published in Materials for Quantum Technology. And well, it was done with both Carlos and Maria Jose, as well as me, of course. So let's start with the motivation for this work, which in the end is to find long-range links between spin qubits. We know that the exchange interaction is very fast and very efficient for spin qubits, but it's short range. And there are very nice proposals of using shuttling in quantum dots to extend this range. But if you want to go even further or even hybridize with different technologies, you should try to use circuit QED, which is also used in other platforms, and photons as mediator of the interaction. And the idea here is to use photons as mediators between Hall spin qubits. And this has been done in the past with silicon electrons, with micromagnets. So you introduce a spin orbit, an artificial spin orbit that allows you to couple the photon to the electron spin. More recently, we had this nice work with Hall spins, which don't need micromagnets, so you have a double quantum dot to extend the dipolar coupling, and in this way you can couple the spin to the photon very strongly. Now the question is, can we go further and go to the single dot regime? Because these previous demonstrations required the enhancement of the dipolar coupling through enlarging the wave function, enlarging the dipolar coupling. But in principle, with Hall spin qubits, you could even go to the single dot regime, which with much simpler setups, one dot, one Hall spin. There are proposals in this, like this one from Stefano Bosco and our paper from 3 years ago or so with Vincent Michel. In fact, there is some evidence in silicon nanowires of spin-photon coupling in the single dot regime. Still, it's true that in this case you will get a much smaller coupling, but normally the coherence of single dot loss di Vincenzo qubits is larger than in a flopping mode. So this is basically the idea of this work. I mean, let's look at the single dot regime. What are the limits in this single dot regime of spin-photon coupling with Hall spins? And you know, there were these couple of works from before, but it's true that ever since we have learned a lot about how Hall spin qubits work, and they are affected by many different effects that were not really discussed in these papers, like strain-mediated interactions and so on. We now know that if you move your Hall spin in a strain field, you will see that you get a correction to the G matrix of the Hall. So basically you get a new type of spin-photon interaction if you have a secret QED setup. So we took into consideration all these different mechanisms, and we basically found that there are corrections to the G matrices coming through the spin-photon, affecting the spin-photon coupling. And in total, we find that there are three types of terms. There is the Rashba, which in this case can be inhomogeneous due to the strain field. There is the interaction from the strain, which is what I just mentioned. And finally, we find something that was overlooked before, which is that when you drive your Hall with, even if it is a quantized photon, this driving field changes the spin-orbit coupling. Now, if this spin-orbit coupling is inhomogeneous, and this is the first time we have found this, you actually find a new type of vector potential correction that couples to the photons. And finally, it's not proportional to the Larmor frequency. It's proportional to the cyclotron frequency, if you wish, from the vector potential. Now we find that as it was known for germanium Hall spin qubits, the GTMR component from strain is dominant for in-plane magnetic fields, but for vertical magnetic fields, the dominant mechanism is this new type of interaction. In total, we find that you can achieve spin photon couplings in the few megahertz. And if you go to unstrained germanium, which is something that we consider here, that was very recent, and we find that you can even get to the few tens of megahertz for spin photon coupling, which is pretty neat.